Okay, I got pissed off again because I saw this video and now, of course, Tyler is responding to it. But also, Tyler has his own things I need to clarify, but I've probably already stated it in previous videos. Of course, it would be better if I didn't include. It's time for some more Tyler False reacting to science.
Veritasium. Specifically, something strange happens when you trust quantum mechanics. I mean, after all, does the act of trusting it change the result? It's showing the infinite.
I love that statement. I'm gonna give you some TLDR because I know you've heard me say it before, maybe. A lot of the stuff in this video is, for the most part, actually correct, with the exception of the actual title of the video and the one thing that they say at the end where it takes all paths, having to do with, specifically, will you let me move the slider, please, you bitch? Holy crap. You got this experiment here, and if the, let me make it really clear to you, this experiment here proves that light does not take all paths, but there is some other thing that they're not taking account of.
This magic foil, and I'm gonna put it over here. Oh, and we can turn off this. And now let's see what happens when I turn on the laser. Wait. No way. No way. It works.
Yep.
It works.
That's a dot, honey. If it took all paths, that dot would be a line, and your entire thing was disproven with this video. Thank you! And now if you want to have me look at the understanding and stuff about the rest of it, feel free to watch the rest of the video, but that's exactly proving it is not. That is a single dot. That is a single dot. And you know what that is? For real? That's just a laser dot that is above and a reflection of the in-house casing. There's nothing else to it. It's not all other paths nonsense that they're talking about in this video. That laser thing is so bogus, and it has to do with the direct correlation with just that laser beam thing. And if you did this with different laser beam type sets, yeah, where it's emitted, there's a bit of a light that just goes sort of anywhere, but also all we see is one dot.
Wait, what? Look where the laser is going. Oh my.
Wow, it's a dot. Yeah, it's not going in all directions because it's not a light beam. It's a dot. If it went in all directions, it would be a beam. It would also be a very wider beam as well, because it would have gone in all directions, not just one. You're missing a complete core component of why this is happening in the first place. And this is the proof that you have. It totally disproves your entire argument, sir. But let's go and listen to your argument anyway, because that's what I'm here for.
Time for some more Veritasium. Specifically, something strange happens when you trust
Oh yeah, my
quantum
phone is
mechanics.
charged, so we're
And
good.
after all, does the act of trusting it change the result? It's showing the infinite slit paradox and how they form a uniform intensity pattern. Those of you who don't know me, I'm Tyler
That's
Folsom, a
an
nuclear
interesting
engineer
thing.
with
It
a little
has
over 10 years of
nothing to do
experience in the
with what
commercial
we're
nuclear
actually
powered
trying
industry.
to
From
discuss.
engineering operations to emergency response. I don't claim to know everything there is
Nothing.
nuclear, but I can certainly share some knowledge.
They went off
As a
the rails
42-year-old who has spent most of my
hard with
life
this
studying
one.
physics, I must admit that I had a big misconception. I believed
As
that
we all
every
do.
object has one single trajectory through space.
It does.
One single path.
It does.
But in this video, I will prove to you that this is not the case.
Okay,
It
yeah,
doesn't.
I think I know what he's getting at, but let's see.
Everything is actually exploring all possible paths all at once.
No.
So let's
Kind of like running a Monte Carlo simulation.
start with a simple thought experiment. Say you're at a beach when all of a sudden you see your friend struggling out in the water. You
Okay.
want to go help him as quickly as possible, so which path should you take to get there? The shortest path is a straight line, so you could head directly towards him, but
It's like how fast can you swim, though, relative to how fast can you run?
you can run faster than you can swim, and this path requires more swimming. So alternatively, you could run down the beach to minimize the distance through
This
the
is a great illustration, by the way.
Do you realize that the amount of force something can exert in order to go a certain place, and then how it works in a liquid? This is just like if you were using a rocket engine, for example. It's a fixed amount of energy. Well, guess what? Electrons have a fixed amount of energy. Photons have a fixed amount of energy. That's why C is a constant in certain atmospheres. And then as you change the different substance that you're going through, it changes its constant because of how it's able to exert itself in that substance. It's almost like it's got its own little propulsion unit, which it does, because it's exciting the electromagnetic field itself, and that is what causes it to go a certain distinct distance. I just skipped to just totally being like, just stop. I don't even want to listen to your argument. I just want to say mine. But I will listen again.
Wow, can totally relate. He's explained, because this stuff can get pretty complex, but this is so grounded.
But
Depending on how deep the water is, you could technically end up jumping into the water and then go through the air much faster than running through the water, technically. And hopefully you don't hit like a rock or something. Forget it.
now the total distance is longer than it needs to be. So the optimal path, it turns out, is somewhere in between.
Okay,
The
sure,
path
yes.
of least resistance, or the path of least action, to use what he said in his previous video on this topic, which if you haven't seen my reaction to that, I'll pin it down in the comment below.
Precise, it depends on the speeds at which you can run and swim.
Uh-huh.
Now, you might recognize this mathematical relationship because it is the exact same law that governs light passing from one medium into another. So, light also takes the fastest path from point A to point B. What's weird about
It
this is
happens
that
to.
as humans, we can see where we want to go and then figure out the fastest route.
Its path is designed based on its capacity to move in that atmosphere. And so the fastest time it could take from point A to B. But there are some ways of making paths that just naturally, like in that they did that sugar emulsion and it made a spiral of light. Clearly it would be a lot faster if the light would just go straight through the tube, but with all the stuff that it's going around, it just bounces off stuff with the same refractory index as this. So it is being pushed into that direction based off of the total velocities of all of the different parts, and the interactions of them compared to the sugar crystals. If I'm not mistaken. Like bouncing a ball in a billiard pool table, the light goes through and bounces precisely. It doesn't have any deviation, so it will just predictably and perfectly every time bounce directly in that spiral pattern, leading to the end being whatever light you end up with at the end. Ironically. And it does not take all other paths. It specifically makes that spiral that is predictable and obvious, and only one of the ways that it could have gone. All the other parts that are adjacent do their own thing, and that's why you have different parts bouncing and doing their own different specific things, making that spiral change as you turn the dial. We've seen that video. We're going to ignore the fact that he made that video to make this one, talking about all paths, as if it actually takes it, which it doesn't. Like any billiard table or pool ball, you push it one way, it goes that way, and it'll bounce based off all the stuff that makes it bounce, and it does it once, and that's it. And where it ends up, that's where it ends up.
But light? I mean, how does light know how to travel to minimize its journey time?
You can always ask it. You can always ask the neutrons in a nuclear reactor, but they can't tell you anything because they're neutrons and don't speak.
Now, here is where my misconception comes in. I shine a laser beam. The light just goes in one direction. I throw a ball. The ball just goes in one direction. You know,
Sure.
I would have answered, there is nothing strange about this. Light sets off from point A in some direction, and then a little while later, it encounters a new medium. And due to local interactions with that medium, it changes direction, ending up at point B.
Yeah.
If you later find that of all the
On an
possible
individual
paths,
basis.
light took the shortest time to get from A to B, I wouldn't think it was optimizing for anything. I would just think that's what happens when light obeys local rules. But now I will prove to you that light doesn't set out in only one direction. Instead, it really does explore all possible paths.
And what you're seeing
really
is where
doesn't.
most of it decided to go because it was the easiest. It's a shame you can't run that way when you're rescuing the guy from drowning.
Any
unless you knew the
individual
multiform
photon
technique.
will not
The same
take
is true
any
for
other
electrons
path
and
aside from
protons,
one it is
all
given.
quantum particles. So the fact that we see things on single, well-defined trajectories is, in a way, the most convincing illusion nature has ever devised. And the way it...
The fact that you're calling it illusion makes me not trust you ever on this topic. You're done with this topic. I can't listen to you and take you seriously because you're off the rails. Not okay way. I am restricting my language, but you are off the rails, sir.
works all comes down to a quantity known as the action.
True.
In a previous video, we showed how
Photons literally use their own bodily mechanics to make themselves push themselves through the electromagnetic field because of their mass being so small they go at the speed of light. There's nothing else there, and there's nothing else to consider. And then that light, because of the electromagnetic interference in other objects and physical interference in other objects, they have a specific amount of speed that they can do in those objects. And again, individually, if you were to be so precise that you are accurate to the photon, you would get predictable results that are perfect and never deviate, don't go in all these different paths and anything like that. We have never been that accurate. We will never be that accurate. It's a bold statement, but it is extremely unlikely that we will ever be as accurate to make complete one photon and then another photon, and it will exactly go precisely 0 deviation anywhere else. But the point is that it does. It just goes there and ends up where it ends up, with no other random mystical stuff in there. And I'm so upset at you for communicating this, because you're trying to put some kind of weird mystical thing into this, and it does not work that way.
An obscure scientist, Maupertuis, made an ad hoc proposal that there should be a quantity called action, which he defined as mass times velocity times distance. And he claimed that everything always follows the path that minimizes the action. Hamilton?
Everything follows the path that minimizes the action. Everything follows the path that utilizes their own ability to influence in the most way possible. Is the most that they are capable of, based on their size, based on everything else. It is the maximum.
Later showed that this action is equivalent to the integral over time of kinetic energy minus potential energy. Action was useful and an alternative way of solving.
I've actually never seen kinetic energy written as T. I just always wrote it out as KE, but I can understand how that could be more confusing because it's not two variables, but to each their own.
Physics problems, especially when Newton's laws get too cumbersome. But then, around the turn of the 20th century, action showed up at the heart of a scientific revolution, the birth of quantum mechanics. It all started with electric lighting in Germany.
Think about what it's like in the 1890s, right? Electricity being more widely available, at least in urban centers. Things like, light bulbs. They were new. They were literally the hot new thing.
Germany wanted to replace all their gas streetlights with electric light bulbs. So an important question was, how do you maximize the visible light given off by a hot filament? Scientists at a German research institute, the PTR, studied how much light different materials emitted as a function of temperature. At low temperatures, each material gave off its own characteristic spectrum, mostly.
Here's the thing, though. You don't need temperature in order to emit light. I'm just going to hold you there for a minute.
In the infrared. But above about 500 degrees Celsius, all materials started to glow in the same way, with an almost identical distribution of light. The hotter the object, the more energy was emitted at every wavelength, and the peak of the distribution shifted to the left.
But they still didn't understand how it worked theoretically. So that was sort of the next step, right? Because if you can understand how it works theoretically, then you can use that theory to potentially design new products.
It's fascinating how you notice some of these concepts, and here I guess we're getting into talking about black body radiation, or light given off by an object based off its temperature. Note that this is the visible type of radiation on the spectrum. Black body radiation is not ionizing. But how you observe some concepts and by just tinkering around with it, and then you kind of have to work your way back to theory.
They started.
So why do I say that you don't need heat to make light? Not all light generates heat. There's light spectrums that are potentially so low that they won't generate heat. Like, you go on the high extreme end, yeah, they're gonna generate heat, but on the lower end, below microwave, the other thing is the weird concept of how much light the moon is able to give, and can you turn that into a laser to make heat at all? And apparently there's heat in light, but the moon is too cold or something. it's about parts per million on how light reflects off the moon, and then that over distance, it ends up being some cold light. It's there, and it's just not making a lot of heat. But that's because it's such a large surface, but altogether it's not really giving off a lot of light. It's a lot that when the moon's high in the sky, yeah, you can see the whole night sky, but you're still not getting enough light that you could recombine all of that light and even make heat. There's videos on that, although they're wrong.
By imagining the simplest object possible, one that would absorb all light that falls onto it, and perfectly emit radiation based on its temperature.
Okay, that's the definition of a perfect black body, which doesn't exist, but you can approximate it for stuff like stars. And that's one way to estimate the surface temperature of the star by what color it is. Know that the surface is way, way colder than the core, because the core is where all the nuclear fusion has happened.
They came up with a hole in a metal cube. This hole is a perfect black body because any light that shines onto it will go straight in, bounce around inside, and eventually be absorbed. But this also makes it a perfect emitter. Any radiation inside the cube can escape through the hole unimpeded.
A metal that's a perfect heat conductor, apparently. All right.
Theorists reasoned that electrons in the walls of the cube would wiggle around emitting electromagnetic
I'm not worried
waves.
about this part.
These waves would then bounce off the other walls. When you have two waves of the same frequency, where one travels to the right and the other to the left, they can interfere in such a way that they create places where there's no wave amplitude, those are nodes, and places where there's maximum wave amplitude, the antinodes. Waves like this are called standing waves because they don't really move left or right. And inside a cavity, given enough time and reflections, it is only these standing waves that survive. All the other ones just cancel out. So a sort of order emerges from the chaos. In 2 dimensions,
The idea of all these waves being in the same orientation in this box is, one, absurd, because that's not how that works. It's bouncing all over the place. And 2,
standing waves look something like this.
Real cool.
For shorter wavelengths or higher frequencies, you can fit more and more different vibrational modes inside this cube. So that in 3 dimensions, the total number of modes is proportional to frequency cubed, or 1 over lambda cubed. The expectation was there would be more and more waves inside the cube the shorter the wavelength. This led directly to the Rayleigh-Jeans law. At longer wavelengths, it matched the experimental data pretty well. But at shorter wavelengths, the theory diverged from experiment. In fact, it predicted that at the shortest wavelengths, an infinite amount of energy would be emitted.
Okay, now we're getting into the ultraviolet catastrophe, and hence he made the color violet. That's very nice and subtle. I appreciate that. With, of course, the solution. But back then, using this classical principle, you didn't realize that energy was quantized at certain points, and you didn't have this sort of phenomena. Which is good, because that was the case, the universe wouldn't exactly work very good.
This is just how we learn about
and you wouldn't be able to get all the wonderful energy you get from nuclear power plants, and all the other types of radiation, which were just being discovered at this point in history.
This, for obvious reasons, became known as the ultraviolet catastrophe. The person to solve this problem was Max Planck.
But Planck almost didn't make...
The thing is, explaining how we learn about how light works throughout the aeons technically is a lot of filler.
Take it into studying physics. Because when he was 16 years old, he went up to his professor and asked him, well, I could do a career in physics. To which his professor responded that he'd better find another field to do research in, because physics was essentially a...
Yeah, it's like how the Truman Show, he was like, oh, I'll be an explorer. We've explored pretty much everywhere. No, we haven't. If I can't explore like all of the islands, then and get new islands, I'll explore under the ocean, under the surface of the planet, or something.
Complete science. You know, there was just a few.
Or in certain biomes where no one has dared to go because it's like, I don't know, a volcano or something.
Tiny little problems
Don't go into a volcano.
that they had to clean up.
That's what's crazy, and it's usually just on the precipice of new discovery. Kind of like when
It's
Lord
funny
Kelvin,
because
a thermodynamics
there are
expert,
more
said that heavier than air
unsolved
flying machines
things
were
than
impossible.
just a
And by
little.
heavier than air, I mean things that aren't like hot air balloons. In 1895, and 8 years later, two guys that owned a bicycle shop proved them wrong.
I love that.
Besides that, it was over.
It's like the
But
Bumblebee
Planck
conjecture.
didn't
The
listen.
Bumblebee already does
By
it.
1897,
Yeah, you
he
gotta
was a
question
professor
that.
himself,
conjecture
and
is
for the next 3 years, he struggled to find a theoretical explanation for blackbody radiation. He tried approach after approach, but no matter what he tried, nothing worked. He said, I was ready to sacrifice every one of my previous convictions about physical laws.
My prediction and idea with regards to an object that emits heat based off of the fact that it turns that lovely orange and whatever is that all the different light spectrum emitted, if it is emitted all at once, is able to overlap. All the different waves are able to exist, moving throughout, as long as they're at the same similar frequency. Their amplitudes can all change. Something. And multiples of amplitude.
Then, in a quote, act of
Kinda have to.
desperation, he did something no one had thought to try. According to classical physics, the energy of an electromagnetic wave depends only on its amplitude, not its wavelength or frequency. And it could take any arbitrary value.
Right.
So any
Yeah.
atom could emit any wavelength of light with an arbitrarily small amount of energy. But Planck tried restricting the energy so that it could only come in multiples of a smallest amount, a
Sure.
quantum. And he made the energy of one quantum
packets.
directly proportional to its frequency.
I wonder if quantum mechanics would seem as intimidating like it is to so many people if you just use the phrase packet mechanics.
E equals hf, where h is just a constant. Think
I mean, it's just about the smallest packet based off of whatever thing you're working with exactly.
about what this does to the radiation coming from the black body. At a given temperature, the atoms in the cavity have a range of energies. Some have a little bit, a few have a lot, and most have their energy somewhere in between.
Okay, normally I see this little diagram with the
And some
little
of that is
bunches of
gamma
together,
radiation.
the blues and the reds is just the nuclei. But here we're talking about straight from the atom, that is to say the whole structure in addition to the nucleus, assuming we're still just talking about UV at this point.
For long wavelength, low frequency radiation, the energy hf of one quantum is small. So all of the atoms have enough energy to emit this wavelength, and the spectrum matches the Rayleigh-Jeans prediction very well. But at shorter wavelengths, higher frequencies, the energy of a
Gets
quantum
off.
increases. And now, not all of the atoms have enough energy to emit that wavelength. This is why experiment diverges from
I mean, if you think about it, you're dividing by something with wavelength raised to the 4 power. So when wavelength gets really, really small, then yeah, it tends to infinity pretty
How the
quick.
intensity
classical
of the
prediction.
light comes
The
from the
spectrum
atoms.
peaks and then starts to
Not-
fall because fewer and fewer atoms have enough energy to emit one quantum of that radiation.
Yeah.
And there comes a point when none of the atoms have enough energy to emit one quantum. So here, the spectrum must drop to zero. With this approach, Planck got a new formula for the radiation spectrum.
There you go.
Now, all that was left for him to do was to tune the parameter h, and when he did this just right, he got his formula to match up perfectly with
Make
experiment.
it really small.
But he was sort of troubled by his own formula because to him it was just a mathematical trick. He had no clue why it worked. It was purely formal. And most importantly, he had no clue what this h represented. I mean, he had introduced a new physical constant without any reason.
It's interesting how, if you're not quite sure about something, you put a little placeholder there to explain, because to make your theory work based on observation. There's another example like this that showed up in nuclear reactor theory. There's a constant in a thermal reactor, so a basic non-fast spectrum nuclear reactor. It's 2.07. People had no idea why it was 2.07, that's just what showed up based on experiment. That's known as the neutron reproduction factor, or the number of fast neutrons produced per thermal neutrons absorbed. And it's used in the four-factor formula that basically tells you if you have a self-sustaining fission reaction or not. Now, as the technology matured and people knew more about neutron energy distributions, which involved spectroscopy, just took 2.7 as, oh yeah, it's that thing that sort of works.
He wrote, a theoretical interpretation had to be found at any cost, no matter how high. So from that moment on, he dedicated himself to finding one. He later reflected that after some weeks of the most strenuous work of my life, light came in the darkness, and a new, undreamed of perspective opened up before me.
He introduces what we now call Planck's constant. He introduces what we now call Planck's constant, and it has the units of action. Planck's constant h is a quantum of action.
Planck later...
It's just how much a tiny little thing is able to push on the rest of the stuff to allow it to move. Electrons just simply do that. That's why they orbit a proton without falling in. They don't just magically hover in that orbit. You gotta keep on shooting out your propellant in order to keep it in orbit around the Earth. Well, the electron simply does this passively. And that's crazy and fun and cool. You are made of perpetual motion, basically.
It proposed that anytime any change happened in nature,
all about unit cancellation, there it works.
be some whole multiple of this quantum of action.
So it's kind of spooky, this breakthrough that starts the ball rolling toward quantum theory brings action in, not energy and not force, action. Gives you a hint.
Yeah, because it's the amount of effort you can put in. It's not like energy refers to perhaps potential or kinetic energy. This is the capacity to do work, not in these conditions how much potential energy or whatever else stuff like that. It's more of, okay, well, we have a rocket with this much configuration. It has a specific power rate that it can go this fast, not faster, because we can't design it to go any faster than that. And so it does that. That's its action. And the moment that, like a person who has trained to go, say, 10 kilometers an hour for their run, which is not fast, but let's say they did that physically, strenuously, and whatever else, as much as you want to, there's a limit to what that person can do. That's your amount of action. And if they train more, maybe they can increase that. But a proton and an electron are fixed material in space. They have only a certain size, only a certain action. That's all they can do.
Just like the neutron reproduction factor defining how your reactor operates or doesn't.
At first, the quantum of action got little attention. That is, until a 26-year-old patent clerk came on the scene. In 1905, Albert Einstein claimed that Planck's theory wasn't just a mathematical trick. It was telling us that light actually comes in discrete packets, or photons, each with an energy hf. Einstein
really cool
used this insight to explain the photoelectric effect.
I love the circle because it just shows that they're in packets. You think people should call quantum mechanics packet mechanics?
How light can eject electrons from metal, but only when the frequency is high enough. If the frequency is too low, no electrons will be emitted, regardless of the intensity.
That's because the kick speed of its frequency versus this stuff about how electrons orbit is needing to be in phase. If it's not, it doesn't kick.
The idea of quantization spread. 8 years later, Niels Bohr was trying to understand how an atom is stable.
It's like if you were to try to snap a spring. If you don't put in a certain amount of force, it'll just bounce right back. But if you put in just enough more force, the spring snaps, and the electron is shot out into space.
It has a positive charge in the center and negative electrons whizzing around it. Why don't they just spiral into the nucleus, radiating their energy as they go?
And what he wants to do is, he says there's something fishy about something being, that seems to be the new ambiguous weirdo lesson of the new quantum of action.
They not only have their own energy, but their own repulsion of the positive. It's like they're working with the electromagnetic field to specifically give a certain amount of force. Let me moving on.
Bohr realizes that as the electron goes around the nucleus, it has an angular momentum. Mass times velocity times radius. So angular momentum has the same units as action.
And so what he decides to do...
In other words, the electron is only able to push so hard, so that's how far it's able to orbit. And no further unless you add more energy to it. That's why it jumps up a certain amount based on the amount of energy you add.
...is discretize the orbital angular momentum for no good reason. He says, let me slap that on and say angular momentum of the electron can only be in 1 unit, 2 units, 3 units of the same quantity.
And it's amazing how electrons are seen as this orbit, but we say that's like a cloud, and we don't think of it as a proper discrete orbit, even though when we add that extra energy, we do get a discrete bump up in orbit radius. And yet we say that the discrete orbit doesn't really apply, except for the fact that it does, except for the fact that, again, electrons are moving at 22 quadrillion atomic width per second. It's a huge number, or 2.2 million meters per second, or as they actually say it, 2.2 thousand kilometers per second. What a stupid unit.
H, and because it's talking about motion in a circle, the factors 2 pi come in, so it's really nh over 2 pi, what we now call nh bar.
Right.
This comes out of nowhere. There seems like absolutely no good reason why angular momentum should be quantized.
Try it and see what happens.
But by doing it, Bohr finds the correct energy levels of the hydrogen atom. When an electron jumps from a higher orbit to a lower one, the energy difference is given off as a photon of a particular color of light, exactly reproducing the hydrogen spectrum.
If you hit it with enough energy, you can actually have the electrons eject entirely. That's what's known as the photoelectric effect, rather than just... But it could also be a smaller amount and just go from one state to another.
And that was...
I'm drawing a blank here, but is the photoelectric effect the amount where the electron is emitted? Because, yeah, the moment that you put in so much energy that it literally can't even stay in the orbit, then of course it's going to just zoom off.
A pretty startling thing to have fall out. I think that really was compelling. Take some quantity with unisaction and apply some, again, kind of ad hoc discretization or quantization to it.
Now, although it worked
I
spectacularly,
think it's funny, again, how they just tried it and it worked.
no one could make sense of it.
Yeah.
That is, until 11 years later. For his PhD, Louis de Broglie was contemplating the recent discoveries in physics. And his big insight was that if light could be both a wave and a...
Remember, we're going over everything to do with light, energy, electrons, all of this stuff, to think about only one topic, really. Which has nothing to do with anything we've talked about so far.
particle, then maybe matter particles could also be waves.
Well, I've stated in other videos, photons are particles, flat out. Electrons are particles, they just straight up are. Tiny little bar magnets, dipoles as you say, and they literally work like a fluid. But it's not the electrons that are doing the interference pattern. It's the electromagnetic field that is around the electrons that makes the pattern. The field is literally a subatomic or smaller than an electron based liquid, is everywhere. It ripples out in front of the electron as it goes through the double slit experiment. It ends up making the interference pattern before the electron gets there, and that's what makes it go in the path that it would have gone. We'll get there.
Suppose that everything, electrons, basketballs, people, absolutely everything has a wavelength.
That's true, but using de Broglie's equation, it's going to be something like 10 to the minus 35 meters. So you do, but not really.
And he defined this wavelength analogously to light, as Planck's constant divided by the particle's momentum, or mass times velocity.
Right.
Because Planck's constant's already a really small number, so adding in your mass and your velocity, yeah. And that's like it.
Planck's constant is the smallest localized, but obviously you can make measurements smaller than Planck's constant if you go out far enough with a certain angle, or any angle. You end up with tiny deviations capable of being a measurement smaller than Planck's constant, but as for physical phenomenon, Planck's constant is good enough.
Numbers that are smaller than Planck's constant, but for things that have a really small mass, sure.
Now, if an electron is a wave, the only way it could stay bound to a nucleus in an atom is if it exists as a standing wave. That requires that a whole number of wavelengths fit around the circumference of the orbit.
It has been noted multiple times in my videos, this picture of electrons in their orbits and that shell that we notice, and then it's the same thing but from its side. It's not a standard like stable standing wave. It is a constantly fluctuating, changing its orbit with small deviations so that it keeps on rotating its orbit as it's going around. Pretend the circle has like a fraction of a degree off instead of being straight. You get the correct idea. It goes around in circles, 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 circles.
Have one wavelength or two wavelengths or three and so on. So the circumference 2 pi r must be equal to some multiple n times the wavelength. We can sub in de Broglie's expression for the wavelength to get that 2 pi r equals nh over mv. But we can rearrange this to get that mvr, the angular momentum, is equal to nh over 2 pi.
That is precisely Bohr's quantized angular momentum condition.
Yes.
But now we have a good physical reason why it's quantized. Because electrons are waves, and they must exist as standing waves to be bound.
It's quantized because electrons can't give off more energy than they physically have the ability to give. There's nothing more to do. So, yeah. This? Standing waves? No. No.
In atoms.
Because they want to have constructive interference on a stable orbit back.
And this is also, I mean, kind of eventually lead to the electron cloud model where it's all probabilistically driven, as in.
And it's a cloud model. It's not probability driven because it's literally quadrillions of echoes of the same electron every second. Because it goes around quadrillion times in a second based off its speed. That's why I say 22 quadrillion atomic width per second, because atomic width, if you think of if the atomic width is 1/10 of a nanometer or 10 to the minus 11 meters, right? You end up with, okay, that compared to the speed of the electron, you end up with 22 quadrillion. That translated into the number of times it would go around an atom, and you end up with around 5 quadrillion times per second. That's crazy speed. That's why it looks like a cloud.
The electron's not in this one neat little orbit that goes around atomic nuclei.
That's because it's literally interfering with itself, going around so many times that it has certain phases through its own lifetime. And that cloud, those patterns and everything is about how it's changing orbit constantly. And fluctuations are based off of its tiny deviation from a perfect orbit. Because if you had a perfect orbit, you'd be constantly hitting yourself. So instead, you have to move to the side a little bit. The angle that you move to the side a little bit is basically similar to that of the width of 2 electron.
Nah, it's like, it's over there. It has a greater chance of being in this specific spot, but it could be over in that other specific spot.
Again, if you're accurate to the 1 quadrillionth of a second, you'll get a good estimate of where the electron was at that 1 quadrillionth of a second. Since then, it moved into all those other positions.
Yeah.
That's pretty good. You get a dissertation out of that. That's pretty good.
It is this
Sure.
wave nature of
that.
quantum objects that means they no
Hey there, I'm Media.
this wave nature of quantum objects that means they no longer have a single path through space. Instead, they must
This is where you go, again, way off the rails.
explore all possible paths.
It's not that the electron explores all possible paths. It's that its physical motion through space literally inhabits all lot of possible area around the atom as much as it actually can. Different positions every quadrillionth of a second, interacting with its own electromagnetic field, its own electromagnetic influence. And that energy is pulsing and crazy and not just a single circle, but many circles all over the place. And they can bunch up, and they can... It's a lot. When it changes from being a circle like this to a circle like this, or a circle like this, or a circle like this, that's how you get those different patterns. Because it's offset. It has to change constantly. And if you're going that fast, yeah, you'd have to keep on moving to the side to avoid yourself. Because every second you still exist where you started. And then you'll hit yourself again and again and again and again and again and again and again about 500 trillion times. 500,000 billion times.
Now, I have thought about and taught the double slit
Don't make me vomit.
experiment hundreds of times without fully realizing this implication.
In the double slit experiment, I feel like the mental thing that I'm doing in my head is like, okay, well, the beam is not perfectly straight, and of course it's going to intersect both of those slits, because they're really close together, you know?
But then I heard this story about a
If you don't talk about electromagnetic fields with the double slit experiment, you get an F immediately.
professor teaching the double slit experiment, and it makes everything so clear. So the professor
gets
starts
that.
by explaining the setup. Electrons are fired one at a time through two slits to be
Right.
detected at a screen. Now,
How could they, in any amount of fluid dynamics, interfere with each other? They can't, because they were fired one at a time, with intervals between them. There's nothing else there. It's not the same as water, where all of the water is near each other and able to interfere with each other. So what's doing the interfering part? It's not the electrons. It has to be the EM field itself.
Because you can't say for certain which slit the particle went through, quantum mechanics tells us it must go through both at the same time.
Sure.
It doesn't.
So to get the probability of finding a particle somewhere on the screen, you simply add up the amplitude of the wave going through one slit with the amplitude of the wave going through the other slit.
If you actually track where it went and the interference pattern that you end up in the result of many, you can know the angles, and therefore you would know it can't get to where it was by going through the other slit. Impossible. Because there isn't a path leading there. So it went through the top slit to get there. And according to this interference pattern, it's taking the low pressure zones. Like I've said in other videos.
And square it. But that's when a student raised his hand. What if you add a third slit? Well, you just add up the amplitudes of the waves going through each of the three slits, and you can work out the probability.
The interference wave pattern from multiple slits takes the electromagnetic energy that is going through the slits, makes the paths that it can take, and then you would be able to know, based off the initial down to the electron sized deviation, where it went as it was going and where it ended up. Also, if you had lasers specifically vertical, so that you would know it went through this slit, not this slit, not this slit, that kind of thing, if you could do that, you would, first of all, you would know it only went through one of the slits at a time. Second, you would change where it ends up, but you would know it only went through one of them at a time. And we know this.
The professor wanted to continue, but then the student interjected again. What if you add a fourth slit and a fifth?
An infinite
The professor,
slit.
who is now clearly losing his patience, replies, I think it's clear to the whole class that you just add up the amplitudes from all the slits. It's the same for 6, 7, etc.
And this only makes the pattern that would choose where the electromagnetic interference pattern would propagate and become. Here, we're noticing it becomes a lot of pretty much straight lines. Try to remember that.
But now,
I remember having a few professors that didn't like it when students asked too many questions.
bold student pressed his advantage. What if I make it infinite slits? So that the screen disappears. And then I add a second screen with infinite slits, and a third, and a fourth.
What you're not getting is that the interference patterns would turn into infinitely thin straight lines. And therefore, wherever it ended up hitting the first slit, it would maybe pachinko a little bit, but it would end up pretty much straightforward. Depending on how many layers of, like that, it becomes weird when you add multiple sets of slits, because it's already going on a tangent with one. It would go woo, 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 woo. But it would only do that based off of basic, you could do a pool table. Bouncing.
One thing about the whole infinite slit thing is, like, so do you even have a barrier anymore? I mean, you could still, but it's just kind of funny how you would visualize that for infinite slits within presumably the barrier that where the slits are located must
A light prism does this, right?
also be infinite as well.
The student's point was clear. Even when we're not doing a double slit experiment, when it's just light or particles traveling through empty...
I mean, I get what he's getting at. The light or the electrons or whatever
Or liquid.
are also performing said
Any
experiment
liquid.
anyway.
They must be exploring all possible paths, because
You just went off the rails again.
this is exactly how the math would work if you had infinite screens, each with infinite slits.
No. All the different amplitudes would all constructively and destructively interfere, creating a specific grid pattern of where it is allowed to go. There is force on either side. It would be straight, very straight, narrowed down such that you would get it specifically where it's meant to go. You wouldn't get a lot of deviation as you do with double slit. It would be thinner and thinner and thinner. More and more accurate. That's what happens.
You have to add up the amplitude from each slit. That's just the way it...
The best part is the whole uniform interference pattern that you see. He showed that on the diagram right there. You could extend this to neutron.
Again, the amount of interferences, the amount of waves, it all channels it to high and low pressure zones until you end up with nothing but straight lines of high and low pressure zones. So once it's gone through, it will only be straight through. It'll be channeled directly forward without a sideways deviation whatsoever. It doesn't go off to the side.
Say everyone's favorite RBMK reactor, Chernobyl. Neutrons' interaction with that graphite and its moderators, they can have a similar interference pattern as the double slit, which influences the neutron flux distribution. but I really, really don't want an infinite slit experiment with infinite Chernobyl. Sounds bad.
Works.
Yeah.
According to the story, the student was Richard Feynman. And while the story is made up, the logic is flawless.
Because if you believe in a double slit experiment, that you can tell which of the two
Let's start with a lie, why don't we?
slits the particle went through, then you have to consider the
I
possibility.
don't like.
Anyone making a postulate, whether it's a theory or an idea concept that was in a classroom or in between peers, who cares? The idea was presented, we get it, yeah.
The I believe statement. It's kind
That
of.
it goes through both.
Do you need to believe for physics to work?
By that same logic, anytime any particle goes from place 1 to place 2, you have to consider all the possible paths it could take to get there.
Try to remember this part because I already explained how it was a dot earlier. It would have been a line. And it was a dot. You've disproven yourself at the end of the video. But let's keep watching, shall we?
Including ones that go faster than the
These
speed of
insane
light,
people.
including ones that go back in time, and including ones that go to the sun and back.
I feel like it can't go to the sun and back. You have to restrict it to be local, right?
So the math doesn't do that.
Why?
I mean, you could see that just in the double slit experiment, right?
Light clearly goes from the sun and clearly is shines from the earth, reflecting off the earth, going back to the sun. There's no reason why it wouldn't go to the sun and back. Or vice versa, because it doesn't shine, like you don't shine a light off the sun and expect it to be reflected off. It gets absorbed.
And he mentioned back in time. That's the one that, at least my brain, has a harder concept than going to the sun. I mean, it's just searching for its optimal path. Sure, it went to the sun.
And we'll do light, because then there's no funky business with the speed. If you're gonna say, like, this path
I think that's the first time I've ever heard someone say light as far as no funky business with the speed. I mean, I get what he's saying as far as constant speed is concerned, but usually things involving the speed of light
I don't
get
have
kind of weird.
with this path,
Wait, I do have
and these
copy of this
distances are different.
Right.
And so clearly they can't have the same speed. So you need to consider paths that have different speeds.
Feynman's way of doing quantum mechanics suggests that anything
The electron ends up, when you shoot it, in a gunshot-like splatter pattern when you do double slit experiment pattern thing. So, it ends up all over the many different electrons end up all over the place, meaning the tiny distribution differences from the electron gun to the slit, the interference pattern makes a very large deviation of the paths constantly, and only depending on where they started and where the interference pattern would lead them, that is where they end up. And if that is the fastest time to get there, clearly, if they could go in the, like, it's not a, there's a lot of variability in the electron's pathway. This is a well understood fact.
going from one place to another is connected in every possible way. So, according to Feynman, anytime a particle, a photon, or even a macroscopic object moves from point 1 to point 2, has some chance to take any path. And as preposterous as it might sound, he found that we need to include all these paths in our calculation, where each path is weighted the same.
If that was true, also, you gotta consider what would happen with the LHC, Large Hadron Collider. That damn thing would be like, oh, well, it has the potential of going slightly more this way than we're pushing it, and its paths are crazy, but in general, if we have a strong enough force pushing it all in one direction, we know where it's going.
So why then do we not see all those crazy paths?
Well, that's because we still need to add up their amplitudes.
Yeah.
For simplicity,
This is just like running a Monte Carlo simulation to see your neutron.
You realize if you throw a ball, you don't have to amplitude all the electrons and atoms in the ball. The ball and all of its parts are moving with respect to each other with a certain amount of like we're all in this together. We're all just gonna go, and it depends on like wind resistance and whatever else that makes it turn as much as it do, or in the case of golf balls, how much air just flows right over it.
Flux profile to see your neutron flux profile in your reactor. You use billions, trillions, depending on how powerful your computer software is.
We calculate for wind speed and all that junk.
Fortran 77, so powerful but clunky. But running all these computations is critical for predicting your flux
Macroscopic
patterns,
is
telling
so
you where
much
you're going to
more
achieve criticality, which is self-sustaining fission reaction, and also your dose rate. So I guess you can say plotting all these paths is important in nuclear safety.
imagine we only have 3. We only have 3 paths. Then here's what we're going to do. First, let's take this one. When the particle wave starts following it, we start a stopwatch. It goes around and around very fast.
I wasn't expecting the stopwatch to do that for some reason. Very spastic.
It is hilarious, yeah. But it's like you have to be that fast because you're working with fractions of a second. This is not even fast enough. Imagine it being a blur. That's why electrons look like a blur. I'm just saying.
Stopwatch.
And when it gets to the end point, we hit
Because they're
stop.
going super fast.
We'll do the same for the other 2 paths. And then we add up the arrows, square the result, and that is then proportional to the probability the particle took those paths to get there.
It's an integral.
In this case, the arrow and square are pretty small, so the probability of the particle going from 1 to 2 using these paths is small.
Okay, I gotta ask you, what kind of
Yeah.
Compare that with these 3
what kind
paths,
of
for example.
forces would have to be influencing it to make it go those different paths? And if you don't see those forces there, you wouldn't consider those paths. Like, or depending on the geometry of the particle, why would it just spiral towards the thing unless it's designed to do that spiral? In which case we would know exactly where it would end up, and if we were to move closer, the spiral would be at a different point, and a different point, and a different point. You know what I mean?
Well, now the arrow is
Predictable.
much larger. And this is important. The larger the resulting arrow, the higher the probability of that event happening. Now, in these examples, the stopwatch is not actually measuring time. Instead, it measures something called the phase. Just
Yeah, that's what threw me off. It's like, that's not a stopwatch.
double slit experiment, when a wave takes a different path from point 1 to 2, it will end up there with a different phase. And this phase is what determines the amplitude of the wave at that point. Mathematically, we can write the amplitude, our stopwatch,
Phase,
as
like
e
waves
to the
being
I
offset.
phi, where phi is the phase. As the particle wave follows a path, its phase increases, winding the vector around. So now the big question is, how much does the phase change for each path? Well, to answer that, imagine
Slow-mo guys need to track an electron as it moves through the double slit experiment, get the definitive answer of where it actually goes, and I mean, eventually they'll do it. We're getting there.
we split up the path into many tiny sections, each one so small that it's effectively straight. Then, in each section, the particle wave goes a distance delta x in a time delta t, and the increase in phase is easy to compute. It just depends on the wavelength and frequency of the wave. To find the total increase in phase for the whole path, we just add up all the little phase increases of all the individual sections. But we can
Sure.
sub in lambda equals h over mv from de Broglie, and using E equals hf, we can sub in for frequency.
I love watching his
We can
derivations.
also simplify by writing h over 2.
I wasn't the biggest fan of
Not
proofs,
super
even
bothered
dating
by
as far
this,
back
yeah.
as high school geometry, but I love the way he explains it.
As h bar to get this expression.
You know, when I was in high school, they had me try to take measurements of the roads on a map and then add them all up and be able to tell the total distance that you would have to travel on that road with an accuracy that was, well, good enough. But they didn't say how good it had to be, and I ended up making way too many measurements because I was super accurate. And my deviation was, well, obvious.
Then we can take delta t to the right, and if we make delta t infinitesimally small, then we can replace this sum with an integral. But now dx by dt is just velocity, so we can write this as mv squared.
Right.
Now, we know that in the simplest case, the total energy E is just kinetic plus potential energy. And subbing that in, we're left with the integral over time of kinetic energy minus potential energy.
Yep.
But wait a second, that is just the classical action. So it's action that determines how fast the stopwatch turns. As the particle moves along a trajectory,
Back to
its
least
action
action again.
increases, and that is what increases the phase.
Quantized action, because it's got that little h in there.
And what's important to note is that h bar is tiny. It's about 10 to the minus 34 joule seconds, which is way smaller than the action of any everyday object. That means the
on a
phase of
small
ordinary
scale.
objects on ordinary paths spins around zillions of times, eventually pointing in some random direction.
22 quadrillion.
If you consider a slightly different
So don't rely too much on this when you're
For an
trying to
electron.
save that one guy on the beach.
path, the action may be slightly different, say 0.01 joule seconds different. That doesn't seem like much, but divide it by h bar, and the arrow will spin around 10 to the 32 more times. So again, it will just point in some random direction. This is what happens to almost all of the possible paths. So when you add up the phases, they just cancel out. They destructively interfere.
That's true, but it gives you such a crazy amount of precision, which is, again, why a lot of nuclear engineering programs for things like neutron transport and dose calculations.
Hey, if
use
it's
something
useful, go ahead.
Clunky like Fortran
Still.
77 to do all that for you.
The only exception is for the paths closest to the path of least action. Because
Sorry.
these paths are at a minimum.
Use something clunky like Fortran 77 to do all that for you.
The only exception is for the paths closest to the path of least action. Because these paths are at a minimum. So if you make tiny changes to the path to this order, the action doesn't change.
And so for other paths that are very close to the path of least action, their arrows point in basically the same direction. They constructively interfere,
Converge
and that
on a
is
point.
why those are the paths we see.
This
Oh, for fuck's sakes.
explains how light knows where to go. I mean, it doesn't. It just explores
Trial and error.
all possible paths. For the paths
No.
Same thing with the neutrons.
seeing are the ones that interfere constructively. And those are the paths of least action. So really, this is how classical mechanics emerges from quantum mechanics. It's why a ball follows the trajectory it does, and how planets orbit the sun. They don't really have a precise trajectory. Instead, everything explores all possible paths. It's just that massive particles have large actions compared to h-bar, so that
So you could, just see it as in things that are just getting much bigger. That the classical stuff is a good enough measurement, at least as far as engineering is concerned. I'm not a physicist. Physicists might disagree with me on that one, but
Yeah.
because things like Planck's constant is small, like you said, and things like quantum tunneling become negligible. Like, sure,
Quantum tunneling is like if you consider a diamond, which is just a lattice of carbon molecules, to be like a chain link fence, electrons are easily able to go through the loops in those fences. Because at some point, it's like all of those other orbits around the atoms of those carbons are able to allow the other electron to just pass straight through. Or hydrogen, for that matter.
Sure, I could technically phase through this planet right now via quantum tunneling, but the probability is so ridiculously low, it ain't happening. There's Ehrenfest's theorem on position and momentum for quantum scale products. Basically follows your classic.
It's not that its probability is low, it's that when you make something that's bigger than a single atom, yeah, you're so big, you're not just going through the small little area anymore. You're a big thing trying to go through a small hole. It don't work no more. Quantum tunneling is a small thing going through, comparatively to its size, a good enough hole. Like a balloon going through a lot of other balloons. Kind of squeezes right through, no problem. Your collection of balloons, you're not getting through.
Mechanics when you get to a certain scale. But I guess this is one way of thinking that I
collection
didn't
of
necessarily think,
balloons.
that I didn't really think about before, that essentially these quantum probabilistic outcomes converge to essentially deterministic outcomes.
Don't quote me on the duodecillion.
Which I only really thought of it in terms of things like nuclear reactors, but I guess a lot of things are like nuclear reactors, which I keep seeing in the comments about relating everything to nuclear reactors. So I guess this video proves that doing that makes sense. Huh. I feel a little vindicated in that.
Fluid
Paths
dynamics.
extremely close to the true path of least action survive, which is why they're much more particle-like. If you go to much smaller particles like electrons or photons, the actions are much smaller, and so there's more of a spread in which trajectories they actually end up taking. Now, you might say, I still don't believe you, but Casper has this incredible demo that should convince you 100% that this is really how the world works.
To do it, I've got a light.
And we're back to the beginning of my video, where you disprove everything you just said about multiple paths.
Mirror and a camera. Now, there are infinitely many paths that the light could take. And according to Feynman, we have to add up the contributions of each of them, including paths that go like this.
Here's the thing, though. The light is going in all sorts of directions. Yeah, we see that later on. It itself is not a single thing going in all directions. It's a collection of things. All of those separate things go their own way.
Now, you might say he's crazy.
I'm not crazy. That's what happened. Another possibility is it could come here and go. Or it could come here and go. Or it could come where you'd like it to come and go.
Now, you see, I don't think he's crazy, but then again, I've lived so much of this sort of stuff. Maybe I'm just as crazy. Yeah, that's probably it.
And it can go over here and go, and so on, and so on. And these are all possibilities.
And every single one of these paths has their own little arrow. So what we can do is we can look at all those arrows and see where they line up. And so if I turn on this light, that's exactly where you see it reflect. So that the angle of incidence is equal to the angle of reflection. But now what I'm going to do is I'm going to cover up that spot so that we no longer see the light reflect.
You know, the reason why you see the dot there is because of the receiving end is there, and trajectory of where the light went to where it ends up. If you were to move that observing little camera that you got, you'd be able to see it actually took, yeah, it's light. It goes all sorts of different, like this one light is filling the whole room with light. Yeah, it went everywhere. Not one photon went everywhere. the collection of them then.
And then I'm going to prove that Feynman is right. That really light also goes like this. It's just that most of the time those effects are cancelled out. Now, that sounds impossible, right? But let's zoom into this tiny piece right here.
No, it's obvious that it definitely did go straight down, because the light is shining straight down. Some of the photons were thrown straight down, and they bounced in a way that led up.
Then we see all these different paths, and all the arrows just go around and around in circles. So when you add them up, they all just cancel out. About half of them like so. Well, now when I add up those arrows, you suddenly do see a large resulting arrow. And so if I can somehow cover up this mirror in many, many tiny strips, then I should be able to get the light to reflect like this. And I can do that with this piece of foil right here. On this piece of foil, there are about 1,000 lines per millimeter, and that should be enough to get this effect. So let me turn off the lights. So let's see. I'm going to turn it on in 3, 2, 1. We see it! We see it! Ah! That is so cool. It actually looks a lot weirder than I was expecting it to. I was expecting more like one spot, but there's many, many spots where it's reflected.
So looking at this, we can tell that, yeah, the light from a round source of light went towards all these different positions and bounced back towards the thing with extremely many different types of path that each individual photon could have ended up based off of where they started off and where they actually ended up. Obviously is boom, boom. It is one simple reflection, one simple path. All of the photons from a large many sources of light will do something like this, because they're projected in all sorts of different directions. That's not one photon doing that entire set of thing. That's many.
Ooh,
inconclusive.
Okay. And just to show I haven't been cheating you, right underneath is my finger. And even with the light on, you know, we see the light reflect. And if we remove the cover, then what do we see? Yeah, we see exactly the normal reflection where it's always supposed to go, which is right there. And then
you can even see with the lights on all these stupid little dots that are very faint compared to what they were when the lights was off, but you can still see them because, yeah. And so we know that, yeah, this one source, which is a bulb going out in all different directions, it's not narrowed down at all by lensing by any means, so all those different photons are able to come back in all those different positions discreetly. This makes total sense for a spread out like the sun.
We've got now all these extra reflections, all these extra bits where the pattern just lines up. So very, very cool. When I was talking about this with a friend, actually, he said, yeah, but you're using a diffraction grating. That's kind of like cheating because you get all these other reflections, right? And this light is just going all directions. And so there's one other thing I've been super, super curious to try. I also want to do this with a laser, where I shine the laser right next to it, and then if light does take every possible path, we should also see it come off here. It probably shouldn't work. Actually, I have a laser right over here, and we can see when I shine it, it really does just go to one spot.
Let's see if we can see it already. So it really just goes in one spot, so you say, but
you can see where that spot is. It's right over there, which is about the same place where we had our reflection. And you can also see right now.
Notice that he's having the laser above the covered part of the mirror, which means you can't see the light that is going from the laser itself. That would also show up.
We look at this view, that you
Laser
cannot
housing.
see the laser light at all, right? Like I could see the laser, but I have to bring it down all the way over here.
Yeah.
And then I'm able to sort of see the light. But if I just put it up here, you can.
Notice for a split second you could see exactly that bit where the light was emitting from shine directly at us, even though the light's pointing that way. Yeah, that's because it's not lensed at all.
And see the reflection. Now, what I'm going to do next is I'm going to put
Or it
this
still
foil,
has deviation.
this magic foil, and I'm going to put it over here. Oh, and we can turn off this. And now let's see what
Turn
happens
off the light,
when I
obviously.
turn
You
on
only get the
laser.
results from the laser, and you end up with... Oh, look, it's a dot.
Wait.
It's
No
one
way.
dot.
No way. It works.
Yep.
It works. Wait, what?
Look where the light went, guys. A single point. Real intensity? The single point you end up with. I wonder why. The reflection off of the thing with the laser being there, and the actual laser, why they would not be the same size. Do you know why? I know why.
Laser's going. Oh my
It
god.
actually looks better with a laser because it's just more concentrated.
It actually works. What?
Notice how he moved the laser up and down to where it was pointing, but because of where the light source was positioned isn't changing, the dot remained where it was. I know why that is. How do I describe it? So basically, inside that little laser thing is a disc. This disc will send out a certain amount of light in all directions. That light is coming from that reflection off of the housing of the laser. Has nothing to do with the laser itself. Has everything to do with that housing disc. It's why it's nowhere near as big as the laser beam itself. It's why it's nowhere near as bright. It's why it's nowhere near changing in direction as the laser beam is actually going. Because it's a separate light source than the laser itself. Because if it was taking all paths, we would see lines, not a dot. And we would see those lines change. We're not seeing that. The beam's a beam. It doesn't go infinite paths. I'm sorry you played yourself.
This is definitely the coolest demo I've ever done.
Nice.
So what I was doing is I was holding
You're
the
too
laser.
enthusiastic.
And I can show you right now. I was shining it
You're
down
not
like
subjective.
this, way off, and you could still see
Where the hell is it?
it reflect. But if I take this away,
There it is.
Just the amplitude goes way down.
Okay, hold on.
And if I put this back, it appears.
Yeah, and you see that light? That's where the light is directly on the laser from the thing.
So that shows really that we cannot get rid of the area which gives zero, that it really is canceling out, and if we do clever things to it, we can demonstrate the reality of the reflections from this part of the mirror.
Completely and utterly debunked.
So,
that would
by
have.
extension,
Hold on, stop,
everything.
back up, back the frick up, shut up. What did you just do?
Demonstrate the reality of the reflections from this part of the mirror.
What the fuck is that?
So light, and by extension, every...
What the hell was that? Again, nowhere near the intensity of the actual beam. I swear to God, it's the housing that is around where the laser is being emitted, not the laser beam itself doing any of that junk. It's separate reflections. You should have spray painted that shit black. And you would have had a more less false positive nonsense.
Really does explore all possible paths.
It really doesn't.
It's just that most of the time.
It really doesn't. You totally misunderstood what even you did in your own experiment because you're too excited. It's bad science to do that. Someone who's not too excited would be like, okay, let's try and figure out about this reflection here. What's causing that? Analyze it. Figure it out. That's what I did. And I know it's it's like the... Wait a second, I have the exact analogy. It's a pen, but it'll do. Here it is, right? See how it has that reflective housing around that? That laser beam has the same bullshit around it. It's bouncing, the light off of the beam bounces off this stupid housing because that's how it's designed. And it makes that utter light, but it's not at all the intensity of the actual laser. The laser itself is not doing all those different paths. It's the housing bouncing it in different ways. A second source of illumination that is not being considered or accounted for. Your test is void. I'm sorry. So, your whimsical idea of light taking all different paths, or electrons taking all different paths for the double slit experiment and all that jazz, to try to make it seem like they aren't discrete paths that can be predicted? What exactly are you trying to even say? Hello, dude. What are you watching? I don't get it. What are you explaining? Please help. Dude, I have been talking for over an hour. If you want to know what I've been talking about, you have to pay attention for the whole video. And be here for the whole video. The basic thing is that they have this idea that if you have, for example, a double slit experiment, you end up with the electron maybe going in all of these different paths as it goes from one through apparently both slits at the same time. It only ends up on the other side as one particle, but for some reason it has the properties and ability to go through both. Long story short, it doesn't. It's an individual particle influenced by where it was shot from in the electron gun, and the interference pattern can show you that it will go through only these paths based on the interference pattern, so it'll only end up on those spots. And the deviation is based off of where it was when it was shot from the gun. And no one has an accurate measurement to try to do this correctly. And this example is showing that the two slits would be way wider away from the center of the gun than they actually are. These double slits would be the size of a fraction of the size of the emitter. Otherwise, there's no way that the electron would go through both of the slits. It would just hit the wall there. It's a bunch of stuff. They're trying to say that it goes through both slits, as well as if you have many slits, you go through many slits. And it's a ridiculous nonsense thing, and I have to debunk all of this garbage because I'm tired of people getting bad information. I'm tired of it. I don't care who does the reaction, and then I have to react to their stuff, because when they add things, whatever extra stuff that they put in as their input, if they're right or wrong, I'm going to confirm you or debunk it. That's my job.
Bring it down all the way over here.
Yeah.
And then I'm able to sort of see the light. But if I just put it up here, you can't see the reflection.
I'm sorry. You put it up here, and you're above the dark spot that you've covered with a paper. That's why you can't see it. It's not shining down towards you right now.
Now, what I'm going to do next is I'm going to put this foil, this magic foil, and I'm going to put it over here. Oh, and we can turn off this. And now, let's see what happens when I turn on the lasers.
So why in that ever-loving heck do we end up with the laser being massive and over there, and any amount of reflected light be over here, not at all near the intensity of that laser beam? And I explained it similar to how it's just bouncing off the housing. They falsified their own test, and it's a stupid test made by an over enthusiastic person.
Wait.
Not objective.
No, wait. No, wait. It works!
Yep.
It works! Wait, what? Look where the laser is going!
That's a false positive.
Oh my god!
We're just gonna pretend like nothing.
Laser because it's just more concentrated.
It actually works! What? What?
Again,
this is definitely the coolest demo I've ever done.
Nice.
So
It's
what
a
I was
false
doing
positive.
is I was holding a laser, and I can show you right now, I was shining it down like this, way off, and you could still see it reflect. But if I take this away,
Just sample, see if it goes way down.
and if I put this back, it appears.
So that shows really that we cannot get rid of the area which gives zero, that it really is canceling out, and if we do.
yeah, I'm sorry, you played yourself. That's a false positive, and you're dumb for not knowing about this one instance. You're not using the correct logic about it. You're not considering the alternative light sources, which is how the light reflects in its housing down to the mirror, and how that's the real source of what you're seeing, which is why it's less intense than or less size entirely than the actual laser. If it was the laser is taking all paths, even though it's a goddamn beam, right? If it was the laser taking all paths, it would be just as intense in the other reflections It's not. Because that's not how the housing reflects light. It reflects a small amount. Because it's a convex, it can only reflect a small amount of the actual beam down. And it doesn't matter where you point the rest of it, it only reflects that much. Right? So, it's a false positive, you're over-exaggerating and over-enthusiastic, you're saying light takes all these different paths, when really it only takes one. And you can predict it, you're just not accurate enough to predict it.
Do clever things to it, we can demonstrate the reality of the reflections from this part of the mirror.
That's awesome.
Yeah, no. Also, this bothers me. Hold on, stop. And now we're seeing this. I only saw one light before, now I'm seeing 9. Actually, surprisingly, only 9? Why only 9? And why does it have not at all the luminosity of the actual laser point reflection over there? Why is it this? That's because the amount of light from the convex thing that is around the edge of the laser emitter, yeah, that's shining light also. It's a reflection, not the main source. So all of that is happening, but it has nothing to do with the actual laser and what its path is doing. It got me riled up about this crap.
And by extension, everything really does explore all possible paths.
It doesn't.
It's just that most of the time, the crazy paths destructively interfere. That's because the actions of nearby paths change rapidly.
That's not what
Now, I've
happens.
studied physics for most of my life, and I feel like I never really appreciated how important action and the principle of least action are. But
again, particles like photons and electrons have a certain amount of action because of their ability to influence the electromagnetic field that they're flowing through, and that is it. And considering the atmosphere that they're flowing through, that's how fast light is able to go through, example, water versus air or a vacuum. And it's never a full vacuum because there's electromagnetic fields there. So if you were to make a full electromagnetic and atmospheric vacuum by putting a massive electromagnet demagnetization field in there, light wouldn't even move to the other side. It wouldn't get anywhere because it has nowhere to pass through. But you've never done that test, and you never will. For a while. Because I just said about it. You have to deactivate. You can neutralize the magnetic field, by the way, in a localized area. Just as much as you can guide things towards a magnetic field in a Large Hadron Collider, we have made a ball of magnets where all the magnetic energy was only able to emit outwards, and it wasn't able to circle back to the inside where the other side of the magnet is. So it wasn't able to cycle any more magnetic energy. It became a paperweight, as if it was made out of plastic. But it's made out of magnets, but none of the energy can flow. So try moving light in one of those. You won't be able to, because there is no energy to move it. Maybe. There might still be something, I don't know. But that's as close as you can get to an actual complete nothing's in it space. Put that kind of a ball where all the positive poles are on the outside, all the negative poles are on the inside, and you end up with a zero Gauss. There is no magnetic force from this ball. because it can't float from in to out anymore. It's sealed, basically. Or the amount of flow is extremely tiny, and therefore the amount of electromagnetic energy within that is also very tiny. I don't know if it would actually work to totally negate all electromagnetic field inside of it, but it's the magnetic field would definitely be negated completely, because it has been done.
Now I think I finally get it. And I finally get why if you ask theoretical physicists what they're working on, they'll rarely talk about energy or forces. Most of the time, they'll talk about action.
Nobody in particle physics approaches particle physics from a viewpoint other than least action. But we teach physics historically, and
I mean, I talk about physics all the time without referencing the action, except for to say that knowing the speed of the electron or knowing the speed of sound, for example, that's how long it takes for a lightning bolt strike to be noticed by you, and the speed of knowing the speed of sound and knowing the speed of light, when the light flash will get to you and when the speed of sound will get to you, as well as the EM pulse, which is faster than light. If you were measuring that, you would have 3 different measurements and you'd know exactly when and where that lightning bolt struck, because it can't go, because of the speed of sound. When you get the sound signal, you can only go that far, and it cannot be any further away than that. Because of the light signal, it can go that far and not be any further away than that. And because of the impulse signal, you can go that far and not be any further away from that. You can be really accurate about where that lightning bolt struck and when. Because those compensate, those are totally different values, and you end up with something that's able to pinpoint exactly where the lightning bolt struck. It doesn't matter if you're in a train going in relativistic speeds. You're not going to think that the lightning bolt struck, for example, the one behind you will not. If there's one behind you and one in front of you, you're not going to calculate that they struck at different times if you know how to compensate for those speeds and your speed. If you're not compensating for your own speed, you're not doing real math, and you're failing. Relativity is false.
least action is almost like the new kid on the block for understanding physics. And so, yeah, we build up to it. But
even though it was thought of, the concept of action.
And the whole point is that electrons have their own maintained velocity because of their interaction with the electromagnetic field. That's how that works. It's a particle. It pushes on the electromagnetic field because it's a pump, a dipole, like any magnet. So it has a most amount of force that it can apply. Unless you create a new type of electron somehow, you're not going to change that variant. So it's the most that it can do. Just like any jet engine.
And by someone that most people haven't even heard of.
I think life's a lot easier once you realize this underlying principle.
Because when you do, then all you have to do is write down the correct Lagrangian, so you get the right action, and out come the laws of physics. So you've got a separate Lagrangian for classical mechanics, for special relativity, for electrodynamics, and so on.
It's a single mathematical framework.
Though it doesn't really play well with gravity. Because gravity, you're looking at general relativity, treating gravity as the curvature of space-time, and quantum mechanics.
And space-time doesn't curve.
Which you're looking at strong and weak nuclear, and as well as electromagnetism. And they.
It's funny that you say strong and weak nuclear and electromagnetism, because the strong nuclear force is electromagnetism. Just saying.
They just don't play well. You end up with kind of another ultraviolet catastrophe when you try to quantize gravity, which is why gravitons aren't really
electromagnetism, the electromagnetic field is the graviton. It's just not an interaction between electrons and protons that we're working on, or the electromagnetic type of stuff that we think of when we think of like magnets and metal, but it's the electromagnetic field interacting with literally every piece of material in everywhere. So the electromagnetic field permeates everything. It goes through everything, and because of the mass, you have a certain amount of electromagnetic energy that is flowing to and from you. It literally is a link between this planet and the moon and the sun and Pluto. And it's the reason why Pluto is literally pulling on the moon and the sun. We're not orbiting the sun. The entire solar system is orbiting a space slightly away from the sun because Pluto's pulling on it. How do you think it's pulling on it? It's not the curvature of space-time. That's how you explain local gravity effects. It's a magnetic type of thing, but it's not really magnetic. It's hard to explain because it's the magnetic field. The electromagnetic field. Again, not the transmission of electrons, but a smaller fluid. The same reason why electrons are attracted to protons in the first place. There's an electromagnetic field that does that transmission. But when you get stuff like that, that fluid, expand it to the entirety of the planet and everything, you end up realizing, yeah, that stuff goes all the way throughout everything. It's also the reason why the disks at the edge of a galaxy are able to go at speed and still be connected to all the local stuff and not fling off, even though they're going faster than we expect them to. Because electromagnetic field is what is moving along with them. It's like a record that is moving along, and the solar systems on that edge of the galaxy go along with the electromagnetic field fluid that is moving along. And because they're all of it is moving similarly, it makes a constant wake that doesn't just want to let go of things. I went on that tangent because you said space-time curves and it doesn't, so it's your fault.
In science fiction, because gravitons are the curvatures. Because gravity is the curvature of space-time.
But it's not.
So, and going back to the neutron flux example, that would be like trying to measure neutron flux in a condition where, like, the boundary of the reactor core is, like, pulsating like crazy and the boundaries are changing. Doesn't really work too good. But hey, maybe we can figure that out and actually detect gravitons or something.
Once you've learned,
we already know how to detect your gravitons. We have little pools that do that.
it,
So they sound kind of...
Graviton
you can
detectors
apply
already
it
made.
in
What are you
different
talking
places
about?
in exactly the same way.
No, sorry.
The hunt for the theory.
Okay, neutrinos and other things. There is no graviton. Again, it's just shush. It's the EM field.
With everything, right? The thing that will encompass
But also,
all
no,
physics.
local gravity, and the reason why you're sticking to the planet is centripetal force. The fact that the Earth is spinning so fast and moving through the solar system, we end up with... We are being pushed against the floor of the planet because it's being forced towards us constantly in all directions because of its spin.
In reality, what people are asking is, what is this Lagrangian that can spit out all of the laws of physics in this universe? That's really what they're asking. At the moment, we haven't really found that, right? Because we can sticky tape things together, but we don't know if that's the proper mathematical structure. So that's what...
Look, if I worked with the mathematics of all of that, I could tell you the Lagrangian of the whole freaking theory of everything. I know that the electromagnetic field works like a fluid. I don't know why you don't understand that yet, and whatever else, and all this stuff. You already know how the electromagnetic field is, how electricity actually goes through cables. It's not the electrons are moving, it's the EM field that is doing the major amount of the EM field waves propagate, and they move along the cable. Exciting the electrons at the base is what makes the wave start, and then it just keeps on going because all the rest of the cable also moves similarly to keep it going, and then it has to get re-amplified later on. It's not electrons that are making energy move in the cable, clearly. It's the field doing stuff. Knowing that the field is there, like, you should know better than to say things like this.
People are hunting for.
This was fascinating. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.
So again, a lot of that was filler. A lot of that was trying to explain that it goes in many paths. You could have done that in a 5-minute video, but you decided to explain all of how we understand science about electrons and photons and how they move through space was discovered. I have made videos that are trying. The problem is I could try to make videos that are short enough and whatever else, but I have to respond to, okay, you got this bit, that's fine, that works, that's still accurate. I'm not saying it's not. Like all this stuff about least action, the mathematics about how the quantization of the particles and photons and all of that wavelengths and that, yeah, okay, you got all of that, but you're trying to say that this energy is somehow moving randomly in all different directions, and the answer is, if you were to have sensors literally everywhere that somehow didn't interfere with the path of the electron, you would know where it went, you would know it has to go that way, and it only went that way, and there's nothing you can say to prove that it ever went anywhere other than the one path that it just went. And it's ridiculous that you're making this argument in the first place, Derek. So, yeah, debunked. I'm sorry. It just is. You're bringing a lot of one of the major questions, of course, is I talk about science all the time about electrons and all this stuff, speed of light, relativity, all of these things. How is it applicable and why does it matter? The answer is because if you actually had proper estimates and understandings of what electron does through the air in the double-slit experiment, you wouldn't have to use all these other mathematical things, although you can get accurate results from them. You're trying to ascribe to an idea that is whimsical and silly, and stuff like that needs lots of evidence, and you already proved yourself wrong, so I'm sorry, goodbye. Relativity is false. Curvature of spacetime, false. This nonsense, taking multiple paths. When we know the electron literally only takes one path and it gets there because it bounced because of the electromagnetic field interference pattern that we know is there. It's like you talk about the double slit experiment, but you don't mention the electromagnetic field. It's like you're trying to miscommunicate on purpose. We know you know this information. You might not remember that you know about the electromagnetic field and how it's separate from electrons, but that's there in your head. You've expressed that in previous videos. So how can you be this faulty? I don't know. I just don't know. On presentation, I'll give you an A+. Great job. You make something that looks fancy. But that doesn't mean that you're accurate when it comes to the one thing that you're trying to express. Everything else is just stating what we've learned. But you're trying to get this insight about something off of a false observation, off of a false understanding of how the double slit experiment works. It's just sad. But then Tyler had to say the curvature of space-time thing happens, and it doesn't, and I got even more. I had to go on this other tangent. The only reason people think of the curvature of space-time and time, don't get me started on time dilation, that doesn't happen. To be specific, time being improperly calculated by the way atomic clocks work. You're using a light to bounce back and forth, or a laser beam to bounce back and forth in an atomic clock, and you end up with the faster you go, the further in that clock it has to travel. And you don't compensate for that for some reason. You call that time dilation. Or you say, oh, well, the light that is in a train going whatever speed and the light on the ground are moving at the same rate. The assumption is that the light in the train should be moving faster because it's in a thing that's going faster. So the train speed and the light speed should be added together and they should increase. But my question to you is, why do you make that assumption? Light doesn't give a damn that it's in a train. It is only affected by the substance it's moving through. And the train is just an atmosphere. Outside is just an atmosphere. Light shouldn't move any different. And there should be no random assumption leading to the idea of time dilation. But that's the rabbit hole you got yourself down. You made up something random. If time dilation were to really happen, then as you also are able to move something else at relativistic speeds, which falsifiable, you can't even do that. But let's say you did that with Cherenkov radiation or something. It should be clocked at a faster speed in a train than it is, but also you're moving it in a liquid. The liquid is also moving. That could change the Cherenkov radiation speed because you're moving the substance that it's moving through. But when it comes to air, there's really not a lot of that interaction happening with light. And if you were to empty the train of stuff, then it doesn't really matter how fast the train is going. It's not influencing the light as it's moving. Like if I run to the front of the train going 10 kilometers an hour while I'm on the train, and the train is going 10, our speeds together, compared to the ground, I'm moving 20. Then if I move backwards 10, while the train is moving 10, forward, my total speed compared to the ground is 0. Light doesn't do that. It has an independent from the train propulsion. Doesn't give a damn that it's on a train or outside. Unless the train has some electromagnetic thing that is able to influence how light is doing its motion through the train, it's not going to do anything different. So, yeah, speed of light is still c. The time dilation is like, it's nutty. It's not sensical, and it takes a leap that then they don't compensate for, like Occam's razor says you're supposed to do. Or with great claims needs great evidence, and you just fail too many times with these things. There's no relativity. There's no curvature of space-time. It's a different phenomenon. There is no time dilation. It's a different phenomenon. How this affects things is like, well, if you really understand what's happening in an atomic clock going through, like the way that we deal with satellites right now, we beam the time from a stationary clock that is very perfect, and then it goes up to the satellites, corrects their time because they can't calculate for it. Because screw you, it's too complicated. Not going to make that. But if you were that complicated, if you made a good program, then it doesn't matter if your satellite is going around the Earth or Pluto, it would be doing the correct maneuvers at the correct time because it would know the correct time instead of being incorrect all the time. Because you can't beam time signals over the Pluto and expect it to help unless you're beaming consistently. And then it's going around in the orbit around Pluto and where you have to aim. It's such a tedious thing. Just make a good program and you'll make a satellite that will be able to compensate for its motion and everything correctly based off of, you know, good old-fashioned trajectory math and compensating for stuff. Knowing its surroundings and knowing how to interact with other things. If there are multiple satellites, they know exactly when to do whatever burns and whatever. They won't have incorrect clocks. Incorrect clocks. Time dilation is a myth. It's a myth by lazy people, and I'm tired of it. Make better systems and you won't have to worry about time dilation nonsense. Hence, you'll actually be calculating it correctly. You'll be able to go anywhere you want around whatever gravitational whatever at whatever speeds, and the clocks will be able to compensate for that, know the correct time, and whatever else. And it won't like make an improper burn and end up in the atmosphere or whatever. It's laziness. And eventually that's going to cost them something. Right now, no, apparently, because we have the internet. Yay. You're doing a good job. With the lack of knowledge that you have, you're doing a great job. It doesn't mean that you're not wrong still. And you could be doing better. Like, imagine just how many times per second you have to beam that signal of a stable time reference to every satellite up there. If they could compensate for their own trajectories and everything and have a good internal clock that works correctly, compensating for its velocity and change thereof, as you go, you're constantly decelerating. You have to compensate for that. You're going around a not straight surface. It's a sphere. An orbit. A decaying orbit. And then you rocket suddenly and you have to compensate for that. And it's like, if you had these proper compensation rules, you would know all the different factors that also work on the atomic clock and how it is skewed constantly because of your changing of velocity. And you wouldn't have to constantly beam the light up there to tell the time to it correctly, to know all these different things. Imagine people in NASA believing all of this, all their lives, that time dilation is a thing, the curvature of space-time is a thing, and the moment you try to make an Akubier drive, you're going to move yourself faster than the speed of light and you're going to disintegrate. Because that's what they believe is possible. You're moving space around you and in front of and to the back of you and squeezing it back. And you might even be able to make that drive, but if you ever go near the speed of light, you're going to start disintegrating. And of course you're going to do that with a test pilot, which is just a robot, a drone. It's going to disintegrate. You're not going to get a signal back. And you're going to be like, oh shit, Tony was right. 100 years ago. 50 years ago. However long it takes to make the freaking drive. And if I'm alive to see it, I will look at them and say, hey, you know what? I had that back in 2015. When I originally made the reaction to these things. Where's the evidence of that? Don't make me cry. I've been in this for over 12 years. You know that? I started YouTube in 2008. It's a lot more than 12 years, actually. I started properly in 2012, where 13 was full-time. Science was definitely 2013. Had over 6,000 videos. My own work, all of my gameplay, all of my reactions to science, and everything else. And they shut it down. I don't care how many times I have to repeat myself, I will get the word out about all this stuff so that people are going to stop misinformationing everyone. The fact that I have to make all these different individual reaction videos of all the different times that the misinformation is spread just shows how rampant these mistakes are. There are entire other sets of channels I haven't even looked at yet that talk about science and physics and things, and they quote stuff and they're not accurate, or they're not thinking clearly, and they're forgetting about things. Car moving faster than the wind and all that jazz. I didn't make a sandwich. Goodbye.